the new chapter that is related to deformation of solids, right? The last chapter that we have to complete.
Yes.
So basically in deformation of solids, in IGCSE, you already studied about the concept of the Hooke's law, that load is directly proportional to the extension, right? And there is a constant which is known as K, the spring constant. Okay. And let's suppose if we want to write the definition for deformation. So for deformation, we can state the definition like this. Basically deformation in simple words, we are just talking about if we take the cube. So basically cube is a regular particular shape for solid, and if we try to change the shape size of that cube, so that is known as deformation, right? Basically when a car collides with wall or some solid object, so we say that car is actually deformed over there because the shape size of the car actually changes, right?
Yeah.
So basically the change in the size and shape of an object is known as deformation. This is the basic idea of deformation, and you know that if you just compress the spring or if you just stretch the spring, so basically the shape, the size of the spring actually changes over there, right? And there are two new terms in
Yeah.
chapter that we have to study. Those two terms are known as the tensile and the compression. And new terms will be introduced in this chapter, so we have to know about those terms because in your exam you will find the question including those terms. So we have to know about the basic idea of those terms because they will also ask that define or what is meant by the tensile. So the basic definition for the tensile is when two forces stretch a body. So basically, when we try to stretch our body with the help of two forces, so that whole process is known as tensile, right? Like tensile forces.
Okay. So when two forces stretch the body, that's like the tensile. That's like when it gets tense, like the rope gets
Yes,
tense and it has tension in it.
yes. So basically, same goes with the concept of the tensile. So when we just compress or try to compress the body, so if they are using the concept or the term of tensile, so definitely you need to know about that there are two forces which actually is going to stretch a body, right? Just like the concept of tension. But in tension, we know there is only one force. But in this, we are having two forces, right?
Yeah. So can tension be described as like a force?
Yes. So basically, tensile, tension, all are the concept of forces. All are the different phenomena, all are the different process. But it's still the basic concept remains same. Still, all these terms are known as the forces, right?
Yeah.
And second term is known as compressive. And now you already got the idea of tensile. So compressive will be the opposite of the first one when two forces compress a body.
Okay.
So when two forces compress a body, that is known as the compressive. And when two forces stretch a body, so that is known as tensile. So simply, we consider a spring in a stretched form and a spring in a compressed form. So in the first diagram, forces are going to apply in opposite direction like this, moving in outward direction. And in compression, both forces are again acting in opposite direction, but they are moving towards each other. So this is the concept of tensile and compressive, right?
Right.
Further, if we talk about the tensile, so tensile contain one more concept, because we know that just like the Hooke's law, we try to stretch the spring, or when we try to hang some additional load one by one with the spring, so it starts to stretch, right? So there is a concept of limit of proportionality that we already discussed in the Hooke's law. So same thing are going to be happen with the tensile strength. Only the difference in this situation is that force are going to be applied from both sides. So if we talk about the concept of tensile strength, so we can say that it is the amount of load it is the amount of load or stress a material can handle until it stretches and breaks, right? By the name tensile strength, you got the concept. They're just like the single spring when one force acting on the spring. So till the limit of proportionality, the extension will be directly proportional to the force or the load. Same goes with the tensile when two forces are acting on a spring and both try to stretch the spring in opposite direction. So the tensile strength just give you the amount of load, that how much force or how much load we are applying on both sides of the spring, uh, until the spring will break, or the final limit of that spring until we are able to stretch that spring, right?
Right.
Until it stretches and breaks. So this is the concept of tensile strength. Okay. And if we just take some common examples from some materials of our daily life to just know about the idea of the tensile strength. So some materials, if we take the example of concrete, if we take example of rubber,
What about a rope?
basically rope means it depends upon the material, right? It is like a string or a thread material. So basically we are talking about the different material, like concrete is made up of complete solid, and rubber is made up of like elastic material, right?
What about like what are springs made of? They're made of metal, right?
Yes, we will also discuss that. So if we want to write the values for the concrete, so for concrete, the value ranges between 2 and 5, and the tensile strength or the SI unit for tensile strength will be megapascals, right? Because force per unit area is known as pressure, and the SI unit of pressure is pascals, and capital M means mega, right? 10 to the power 6. Okay, clear? Any confusion?
And no confusion.
And if we talk about rubber, so value will increase because rubber is like stretchable, and it has some limits, so we can easily extend to certain amount of length, then it will break. And in solid, we know that is solid material, just like concrete, we are not able to stretch that solid material, right? So it will break at certain extension or at certain point. And if we talk about human skin, so human skin is more or it has the more tensile strength as compared to the rubber. Okay, and just you mentioned the example of this spring. So normally we are using like iron, steel. So if we list down some other materials, steel, diamond, because when we are working with the glass, so basically we also just melt that glass material, and we are able to use that melted glass material to mold into different shapes, right? So that is also the tensile strength of that material. So for steel, we are having 840 megapascals, and for diamond, 2800 megapascals, right? So these are some values related to the tensile strength of different materials. Okay.
Okay.
And let's suppose if we talk about some graphical representation for different materials. So let's suppose if we consider their values graphically, right? So F represents the load or the force, and E represents the extension, right? So let's suppose if we consider a random graph like this. So this is one representation of the graph. And secondly, if we consider an other formation of the graph like this, and the third one, this is the third representation. So if we talk about the first material, so in first material, you observe that the load or the value of load is very much low as compared to the other graph representation, right? Because the force or the value of the force on y-axis, if we consider the height of the graph, so by that you can easily identify that it has low tensile strength, right?
Yeah.
And this constant part shows you, basically this is the point, or this is the extension, or this is the value of the load, or the extension of the material that is just before breaking, right? So the point where it starts to break, or where you think that it will break at any moment. So that straight line shows you that now a force or the load on that extension is not going to increase over there. So basically now it is going to break into 2 points, or break into two different pieces. So this point represents you that if we apply a little force on it, so your extension will increase in very short interval by the graphical representation. And when your extension very quickly increases in very short interval of time, or that represents you that your material is actually break over there, because when your material is got break, so that represents you the extension in very short interval, right?
Yeah.
So this line represents you the area before breaking. And if we apply little force, so it will break, and you can see that your graph again starts to move in upward direction. It means that your extension will increase very quickly at that point. And in the second graph, you observe that initially we are moving with elastic deformation, like the Hooke's law, because both are directly proportional. Okay.
Right. Okay. But then later on it gets like it exceeds the, what's it called, the point.
Limit of proportionality.
Yeah, so when it does, then it's not being Hooke's law anymore.
Yes. So then no Hooke's law will apply over there. And from the graph, you can easily identify that it has high tensile strength as compared to the first graph, right?
Yes.
And in the third one is just for a simple material, just like the example of a spring, as we already discussed in our previous concept. So again, initially we are having elastic deformation, and at certain point, or after this point, you will get your limit of proportionality, right?
Yes.
So this is the concept of different graphical representation for elastic deformation, right?
Right.
Okay. And if we talk about some new concepts in this chapter, so you already know about Hooke's law. So we just write the formula for Hooke's law, because that will remind you that you have to revise that topic again.
Okay, so the Hooke's law is F equals to Kx, where
Yes.
K is the constant, X is the extension in centimeter, or is
Okay.
it in meter? And
Basically,
is force.
we are actually using a centimeter usually in our calculations, but still, if they are asking about the SI unit, so we use meters, right?
Mm-hmm. And what else? We can also like use the equation like energy equals to half Fx square.
We will also discuss that concept, that is also included in this chapter.
Okay.
So the first important thing is within an elastic limit, because in a spring, when we are writing the law for spring or any body, So it is very important that we have to consider the elastic limit of the body, because after certain extension, Hooke's law is not applicable on that body. So that's why we have to write within an elastic limit of a body, load is directly proportional to extension. And K is a spring constant, and a spring constant means it will tell you about the stiffness of the spring, right?
Yeah.
How soft or how hard material you are using for that spring. So if you're using a very hard, solid, rigid material, so that will increase the constant for that spring. And if we are using very low quality or a very weak material for that spring, so you will reach your elastic limit after very short interval. Okay.
Okay.
And further, the calculation part, if you want to calculate the value of K, so that will be F over X. And according to that, your SI unit will be equal to Newton per meter. So the SI unit for the constant will be Newton per meter.
Okay. So if a spring is more stiff, its K is gonna be more
Yes,
because it can have like the what's it called? It can have more force, but it will stretch less.
yes. And if you try to increase the force or increase the load, so definitely it will deform, right? It will not like the spring that it will have some amount of extension over there, or it will extend further more at certain force. So that's why it depends upon the stiffness of the spring. Okay.
Okay.
So this is the concept of elastic deformation and Hooke's law till now. And further, if we discuss some new concept, like you already know about the questions that you solved in your previous level, that is related to if we are using two spring, three spring. So there is a different concept in that. But now we have to use a proper equation for that. Like if two springs are connected in parallel combination, or
Yeah.
springs are connected in series combination, so then there is a different equation for that.
Okay.
Yes. So let's suppose if you are going to connect a spring in series combination. So series combination means if we connect one spring with the other one like this, so this is the concept of series combination, right? One spring is connected with the other one. So this is the concept of series combination, right? And if we want to write the equation for that, because in series combination you already studied about series combination in electric circuit, that end-to-end combination is known as series combination. And further, if we talk about the parallel combination, so parallel combination will be different. In parallel combination, there is a concept of side by side combination. side by side means if we just connect two springs, like this, if we just join those two springs and connect one load with them, so your extension will be different as compared to the first situation. And for first situation, that is for series combination, your formula will be 1 over k equivalent 1 over k1 plus 1 over k2. K1 means the spring constant for the first spring. K2 means the constant for the second spring, right? And in parallel combination, you just need to add the spring constant for both the springs. K1 plus K2. Clear? Any confusion?
No confusion.
And basically, if we consider two different springs, like we are using two different materials, so then your value of K will be different. Otherwise, if we are using same material, so you know that value of K will be same, that is K1 will be equals to K2.
Right.
So then you just simply combine the values 1 over K plus 1 over K for series and K plus K for parallel combination. Okay.
Okay.
And let's suppose if we consider one quick example to just test the skill for the series and parallel combination of the spring. So in question, you are having a certain setup like this. One, two, three.
So
There
is
are,
it gonna be 1 plus K2 plus K3 equals K
yes,
total?
but if we connect one other spring in the middle, right? So then situation will be different. And if we name them like O, E, Q, R, so these are the
So
symbols for the
so
spring.
is it gonna be like the K of O, K of P, K of Q, right? All of that together. So 1 over that K total plus 1 over the K of R is gonna give you the 1 over K of total.
But if they just give you the values like this, let's suppose if we talk about OPQ, so all are having same spring constant like K, right?
It's gonna be 3K. So 1 over 3K plus 1 over R.
And if we take the value of R as 4K, basically the spring constant for R is equals to 4K. Now your situation is actually changed over there, right? So basically, in this question, you are saying that first we have to add the spring constant for OPQ, K plus K plus K, right?
Like how like in electricity when you have resistance
Yes.
and you
Mhm.
find the parallel first and then you add it to the
Yes.
total.
All these three are connected in parallel combination. So that will be equals to K plus K plus K, that is 3K. And now we have to use the formula for series combination for 3K and 4K.
So 1 over 3K plus 1 over 4K. It will give you 4 and 3. So it would give you 7/12K.
And in this way, we are getting the value of 1 over k. If we just flip the values, so you will get,
Yeah, so it's 12 divided by 7.
so your answer will be equal to 12k divided by 7,
So it's 1.7.
or 1.7k, right?
Yep.
So that is not a big deal because we already know about the concept of the electrical circuits combination. So that is not a very difficult one, because in electric circuits we study with different components like voltmeter, ammeter, resistor, and this is very simple because only a spring is going to be connect only one component. So it is confusion in this topic, right? And further, some new terms are included in this chapter like stress, strain, young modulus. So first, if we talk about stress, strain. So for stress, basically when we apply some force on any given cross-sectional area, just like the concept of the pressure. In pressure, we also apply force on a specific area. So same, we are going to use the concept of stress, but now we are working with different materials and we are talking about their elasticity. So that's why the definition will be like the same for just like the concept of the pressure, but still that we are working with the spring, not like the force, normal external force on any solid object, right? So basically, if we talk about the stress, so it is the applied force per unit cross sectional area of a material. So basically, when you apply some force on any specific cross-sectional area of any material, so that will be known as the concept of stress, right? Or the
Yeah.
tensile stress. Okay.
Okay.
And if you want to know about the formula, so formula will be same, only the symbol will be different. So we are going to use this sigma sign, and rest of the quantities are the old one. So this quantity represents you stress, and that's why your SI unit is same just like the pressure. Pascals, force, area, right?
Yes. I see this in the past paper marking schemes sometimes. They're like stress equals. But
Basically,
isn't stress basically like it's also pressure? It's pressure in
a concept
solid stuff.
of pressure. But in this, we know that in solids, we are not, in the concept of pressure, we are not talking about the extensions or the elastic limits, right?
Yeah, it's just the solid.
Yes, but in this, we are using the concept of deformation, elasticity. So that is,
Deformation is basically like when the hook is like the spring is deformed, like it passes the limit of proportionality, right?
yes, or in simple words, if you are just changing the length or changing the shape or size of any object, so that is the concept of deformation. Deformation means to change the form of any object or any shape.
Okay.
If you are taking a complete square and if you try to compress that square, so definitely the shape will change. So that is known as deform, right?
Yes.
And further, if we talk about the definition of strain, so in strain, we can say that basically stress is like the action or strain is like the reaction. When you know that when you apply some force on any given cross-sectional area, so definitely the length or the extension of that body or that object will definitely change, right?
Yes.
So basically strain is like the after effect of the applied force. Okay. So in simple words, we can say that strain is the extension per unit length.
Okay.
Extension per unit length is known as the strain. And again, if we want to write the formula for strain, so we are going to use the symbol for epsilon for this strain. And again, the basic quantities like extension and length are the basic one. So that is not different from, or that not a new concept, only this symbol is new for in this chapter, and that symbol represents you the strain. X extension, length, right? And what will be the SI unit of the strain?
The strain, it's gonna be centimeter. Wait, extension. So is it gonna be like um
No SI unit, right?
yeah, because the centimeter and centimeter cancel each other
Are
out.
same length. So basically, strain is like dimensionless. There is no SI unit for a strain, right?
All right. It's like a ratio.
Yes. So dimensionless, there will be no SI unit. Okay, it is just the ratio of the length. And if we combine these two quantities, so you will get a complete new quantity that is known as Young modulus. And that quantity is constant for material, or we can say that we have to find out the Young modulus for different material like the spring or the rod or different materials. And we represent Young modulus with the symbol of E. And if we simply define the Young modulus with the reference of the formula, so that will be equals to stress or tensile stress divided by the tensile strain. Stress will be sigma and strain will be epsilon, or you can just simply write FL over AX, right? Because we have formula F over A for the stress, and for strain we are having X over L. And when you just flip the value, so you will get L over X. Okay.
Okay.
So basically, what we are getting from the concept of Young modulus, so we can just simply say that Young modulus actually gives you the measure, or it is the measure of ability of a material, right?
So E stands for energy.
Basically, this E is for Young modulus, right?
But what is Young modulus?
Basically, Young modulus is, if we define the Young modulus, so it is the
It's the
measure.
it's like the stress per unit strain or something like that. So it's the pressure divided by the ratio.
So for Young modulus, you will get the same SI unit pascals, right? Because L and X both are length. So SI unit will cancel out each other, and again you will get the same SI unit. And in simple words, we can say that Young modulus is the ratio of the tensile stress and tensile strain. And in simple words, or the conceptual definition for Young modulus is that it is the measure of the ability of a material to withstand changes in length with an added load. Added load means that how stuff is a material, right?
Yeah.
So basically, Young modulus gives you the concept that the material we are using, that how stiff your material is. So we just compare the stress and strain, the values of stress and strain. That will give you the concept of the Young modulus, right?
Yes.
And further, if we want to write points for the Young modulus, so basically, the Young modulus gives you the information about elasticity of a material in simple words. Or you can simply define as the ratio of stress and strain. So Young modulus is also a very simple concept. I hope that is not much a very difficult thing. Okay.
It's just a new concept.
Yeah.
So,
And further, if we talk about the SI unit, so again it will be
it
equal to pascals.
okay. Can you send all of these notes?
Yes, I will share after the class. And if we want to draw a graph between stress and strain, so definitely the gradient of the graph will give you the Young modulus,
Young one.
because both
So the stress has to be the y-axis and the strain is going to be the x-axis.
yes, because if you are just placing the stress on y-axis or on x-axis, so your graphical representation will be different, because we are taking just the concept of the ratio, right?
Yep.
So basically, stress is like the independent quantity. So if we apply the stress, so then there will be a quantity of strain. So it's up to you that you are going to place your quantity on x-axis or y-axis. So it is just like the graph of the Hooke's law, right? The same graph. Clear?
Yes.
Confusion? Any confusion in this concept?
No.
Okay. So these are some new concepts in this chapter of elastic deformation. And there are a couple of topics, new topics in this chapter that are only left out. Like we just discussed about the experiment of Young modulus, that how Young modulus actually perform the experiment to find out all these values. Then he will be able to use the formula. And we have to discuss the concept of elastic and plastic deformation also, because still now we are only working with the solid deformation. So we also discuss the concept of plastic and elastic deformation, right?
All right.
And we also discuss that how to find out area under the curve for the Hooke's law, or the material that obey Hooke's law or that not obey Hooke's law, right? Because that is a variable
Yeah.
graph. So these two topics are like the new one that we have to discuss. And the last one is the elastic potential energy. You already know about that formula. so that is not like more confusing. So in next class we will try to end up this chapter, and then we only have to solve the past papers.
Past paper.